AP Chemistry, this is day 20, lesson 10, molar mass. This is the solutions video for this lesson. So we start off talking about a couple of questions. Now, I'm putting a copy of this version of the assignment inside of Canvas, and it's giving you space to actually write on the assignment. If I don't give you space, then I'd like you to not write on the assignment. But in this case, you have space. Now, for these, you don't. So generally, I want things to be done on lined paper, but if I do give you space, you can write it on the assignment. The only thing that I'm going to really require you to do are these first four. If you want to do the rest of them for practice, you can do that. So let's go ahead and let's talk about these concepts and what we're doing here. So what is Avogadro's number? It is a special number in chemistry. It's this number. It's 6.022 times 10 to the 23rd. That is also, when we use it in chemistry throughout this course, we refer to it as a mole. We don't refer to it as Avogadro's number, but it's the same thing. And it's a special number. And what's the purpose? It's to give us a big enough number of tiny little particles, atoms, and molecules that we can actually see them and physically weigh them on a scale. We can't weigh a single atom or molecule. We can't see a single atom or molecule. So this big enough number, this is a big number, big basket of atoms and molecules that's big enough to actually weigh on a scale. So whatever number of atoms and molecules we're working with, we multiply it by this number. And that gives us this huge number that we can then see and work with in the laboratory. The question is, why this number? It seems like kind of a strange number, 6.022. Why would they choose that? Why not this? Why not 1 times 10 to the 20th? That's a nice round number. It's also a very big number, and it's one with 20 zeros behind it. Why not use that number? We're going to talk about that in just a second, and you'll have the answer to that question very soon. All right, let's talk about the next two, mass number. So the mass number, and I'm just going to speak these, you can write them. Mass number is the mass of a specific isotope of an atom. So it's going to be a whole number, around a whole number. It's not going to have any decimal places. So it's really the number of protons and neutrons that an atom or a molecule has. And in the case of carbon, let's take carbon for example. If we look at carbon, the most common isotope of carbon has a mass number of 12. Now carbon has to have 6 protons, therefore the other 6 have to be neutrons. So they add up to 12. So each proton and each neutron has an atomic mass of 1 atomic mass unit. So if you have 6 protons and 6 neutrons, that's a total of 12, and that would be the mass number for that particular isotope of that element. Now, you'll notice that the atomic mass is 12.01. Why is that? Because it's the average of all of the mass numbers of all the different isotopes of carbon. So carbon also has, almost all carbon atoms are 12, have a mass number of 12, 6 protons, 6 neutrons. But occasionally, very rarely, you'll find one that has a mass number of 13, meaning it has 6 protons, carbon must have 6 protons, and 7 neutrons. And even more rare is one that has a mass number of 14, meaning that carbon atom has 6 protons and 8 neutrons. And that's the very famous carbon-14 that's used for dating ancient fossils and relics and things of that nature. And we'll talk about that later in the class, how that happens, how that works. It's because that element is that isotope, for example, that isotope is radioactive and so it decays. So we'll talk about that later. But anyway, so the mass number is the mass of a specific isotope. It's always a whole number, like 12, 13, 14. And the atomic mass is the average of all of the mass numbers. And in this case, carbon, since almost all of them are 12, it's just a little bit over 12, and that's because of the carbon-13 and carbon-14. All right. What is stoichiometry? Stoichiometry is what we're going to talk about this week. And it has to do with working with a chemical equation and how we take the measurements that we can do in a laboratory and use a chemical equation with those measurements. So it's the conversion that we have to make between things like grams or liters of gas, or the molarity of a solution, how concentrated a solution is, and getting those into a chemical equation and then coming out with some result from the chemical equation and coming back out again. All right, so that's what the subject will be this week. Okay, first thing we're going to do is practice computing some atomic masses and molar masses. So for water, it's very simple. What you do, you'll get to where you do a lot of these in your head. So here, water has 2 hydrogen atoms. Hydrogen atom has an atomic mass. We use the atomic mass for this straight off the periodic table. 1 oxygen. When we add those two, a single water molecule has a mass of 18.02 atomic mass units. Okay, what's the molar mass? And that's the beauty of this number, and only this number will make this conversion work the way I'm going to show you. Is you take that same number and the molar mass, that's the mass of 1 mole of water molecules. It's the exact same number. It's 18.02. However, the unit of measure, this is the key, is grams, which is what we use, which we measure in the lab on our scales. Our scales are calibrated to measure grams. So the magic of this number, it's the only number that will do this. It takes the mass of a single molecule or atom, in this case a molecule of water, in atomic mass units, that's how many total protons, neutrons it has, and it converts it to that exact same number in grams. And that's, again, that's the magic of that number. No other number would do that. If we use this number for a mole, 18.02, I'm just going to make up a number, would come out to some weird thing like 0.00247 grams. 18.02 AMU to 0.00247 grams. I mean, in other words, there's no relation between those numbers if we use any other number such as this one. This is the only number that makes this convert exactly to the same number there. Okay, I'm going to do peppermint, and then I am going to go ahead and let you do acetic acid and glucose. So let's go ahead and do this. Okay, so the atomic mass of a single peppermint molecule is 156.30. And if we want the molar mass, I'll go ahead and write it out here in the margin. The mass of 1 mole of peppermint molecules, it's the same number, but measured in the unit of measure we use in the lab, which is grams. Alright, so simple concept. Go ahead and do these two. These down here will be optional. This down here at the very bottom is just an example of doing what I just did right there. Okay, so you can move on. I'm going to skip this. I was going to include this in the same lesson. I decided it was too much for one lesson to do balancing equations, so that's the day 21. So you can skip these or do them if you want. The more you do, the better you'll become at them. Eventually, it's like anything else. You'll get to where you can kind of start doing them in your head. But we're going to leave this for right now. So we're going to move on to what's really the main emphasis of this lesson. And that is, I want you, just for this assignment, to draw this table out like this for each of these questions. There's 5 questions. Again, I'm only going to require that you do 3 of them, but I'll give you the answers to all of them. So what is this table telling us? It's telling us that we're going to figure out the atomic and molar masses and even the number of atoms in a particular amount of a substance. So we're going to start with carbon dioxide, CO2. So if there's 1 carbon and 2 oxygens, that produces 1 CO2 molecule, not 3. Don't add those 2 numbers. Just like it takes 1 seat and 2 wheels to make 1 bicycle. So you have parts. These are the parts, and this is the whole right there when you put them together. Now, to get the mass of a single carbon dioxide molecule, you multiply the carbon, you have 1 times 12.01 is 12.01 AMU, atomic mass units. 2 times 16 for the oxygen is 32. And that, now you do add these. You have one weight, a mass, and another mass. You add them together to get the total mass. And that's 44.01 atomic mass units for a carbon dioxide molecule. Carbon dioxide molecule. Now what we're going to do is we're simply going to take these two columns and we're going to multiply them by this. And we're going to come out with these down here. We're going to convert from single atoms, the numbers that apply to a single atom or molecule, to an entire mole, to this number of atoms and molecules. So simply if you say, well, okay, I have 1 atom of carbon, and I multiply by this, I'm going to have 1 mole of carbon atoms. If I have 2 atoms of oxygen, I'm going to multiply by this and get 2 moles of oxygen atoms. And that'll give me 1 mole, 1 carbon dioxide molecule will give me 1 mole of carbon dioxide molecules. Okay, that's simple enough. Again, the magic of this specific number is this next column. That you go from 12.01 AMU for a single carbon atom. If you have a mole of carbon atoms, it's 12.01 grams. Same numeric value, you've just changed the unit of measure. Next, oxygen. The 2 oxygens together is 32 AMU. If you take 2 moles of that, you'll end up with 32 grams. And finally, you can add these together to get this down here. Then finally, the last column. We won't deal with this a lot in the class, but you should understand what the concept is. It asks number of atoms or molecules. So if you have 1 mole, you have 6.022 times 10 to the 23rd. If you have 2 moles, you have 2 times 6.022 times 10 to the 23rd. And again, 1 mole is 6.022. So I want you to fill out these tables just for this assignment, and then eventually this will be kind of routine. You're going to do a lot of calculations of molar masses, because it's really the molar mass, this one right here, that we're really interested in, because we work in the world of moles. I mean, we work in the world of grams, and we need a mole or to have things measured in big bundles called moles in order to have enough grams to be able to work with. Okay, so let's go ahead down here. And I'll show you how I want you to write the answers out here. So, how many carbon dioxide molecules in 1 mole of CO2? So, what you're doing here is really the area of this that we're interested in is what I'm outlining in red here. It's the moles area. We're not interested in individual atoms or molecules. We're interested in working in this world right here. So what I've outlined in red there. So in other words, everything here is referenced to 1 mole of CO2. If I want to have 1 mole of CO2, I need 2 moles of oxygen. But what if I wanted 3 moles of CO2? Well, then I'd need to have 3 times 2 or 6 moles of oxygen. If I want 1 mole of CO2, I need 32 grams of oxygen. But what if I wanted 2 moles of CO2? Then I'd need 2 times 32 or 64 grams of oxygen. It's just like being in the kitchen and cooking and having to scale up a recipe. You have a recipe for 1 cake, but you want to have 10 cakes. Then you have to have 10 times as many of the ingredients in order to make 10 cakes. That's called scaling up or scaling down. You can also scale down. So that's what we're doing here in this assignment, and that's pretty much it. So let's go ahead and do this. How many CO2 molecules are in 1 mole of CO2? So right here, here's 1 mole of CO2, and that's how many moles of CO2, that's what a mole is. That's how many moles of CO2 molecules you have. So here's the way I would like you to write that. You don't necessarily have to write a complete sentence unless you're doing it on line paper. So let's say you are doing this on line paper. There are, and then what you write is the unit of measure and the substance always after a number. So it's molecules. Unfortunately, in chemistry, there's no abbreviation for molecules, but fortunately, we don't use the word very often as far as writing a chemical. We use it all the time, but we don't use it as far as writing in chemical equations. So you write the unit of measure and then the substance. Unit of measure and substance. Now here, this is going to seem crazy to you. Okay, there are 6.022 times 10 to the 23rd molecules CO2 in 1 mole CO2. Now you may say, hey, I misspelled mole. No, actually in a chemical equation, you actually take the E off and make it MOL. So they took a 4-letter word, MOLE, and abbreviated it to 3 letters. But this word, there's no abbreviation for it. You have to write it out. Why they did that, I could not explain. But when you're writing in a chemical equation, mole, it's just MOL, not MOLE. Okay, just a little thing, but you'll see that quite a bit in the rest of the class. Okay, let's keep going. How many grams in 1 mole of CO2? Now, all the questions in this particular set are about around 1 mole of CO2, so I'm just going to do a couple of them. So, in 1 mole of CO2, there's 44.01 grams, okay? And again, this is what I want to get you to get used to. Unit of measure, grams and substance, both of them. Because we could be talking about grams of oxygen, grams of carbon. So you need to be clear what the unit of measure is. Is it grams or moles? And of which substance? CO2, carbon, or oxygen. So it's of carbon dioxide. And again, it's 1 MOL, parenthesis, carbon dioxide. Okay. I'll do one more of these. I will give you all the answers before this is all over. How many grams of oxygen in 1 mole of CO2? So we come up here. 1 mole of CO2 requires 32 grams of oxygen. So you come to the molar mass for grams, and you come to the oxygen row, and they meet up right there. So it's 32 grams. Again, unit of measure and the substance, oxygen. Okay. All right. For the last 3, I'm just going to give you a check figure. Check figure is a fancy way of saying I'm just going to give you the answer, but not show you the calculation. I think you should be able to do these. So I'll go ahead and do that. Okay. And I made an error here. I wrote it in the wrong space. That's what happens when I skip. So this one should have been down here. Okay. So I'll just write this one right here. I'm just going to give you the figure. So this is the answer for this. Please be careful. This is number 4 right here. There, okay. All right. I'll write the answer for number 3 right here then. How many moles of oxygen in 1 mole of CO2? So let's go up there. Let's just do that one. There's 2 moles of oxygen for every 1 mole of CO2. That's what the O2 means. Okay. So 2 moles. Okay, so sorry for the confusion. This answer comes down here. Okay, and then the answer for these two, how many carbon atoms in 1 mole of CO2? So in 1 mole of CO2, there's 1 mole of atoms, and that's it. That's what a mole means. And I'm sorry, I pointed to the wrong row. There is 1 mole of carbon atoms. It's this number. It's the same number, but I should have put pointing to this. That's how many carbon atoms in 1 mole of CO2. There it is. So unit of measure is atoms, and then the substance we're interested in is carbon, and that's how many in 1 mole. Okay, there we go. And finally, how many grams of carbon in 1 mole CO2? There it is right there. This is 1 mole, requires 12.01 grams of carbon. Okay, there you go. That's everything for that. And this answer, of course, comes down here again. Okay, let's keep going. All right, let's do the same thing for water. So go ahead and draw this table. You can freehand it or get a ruler. Or if you print this out, you got this. So let's go ahead and create this table for H2O. Okay, so there we go, and now we're going to do this. Okay, so that completes the table. So we're just counting atoms, 2 hydrogen, 1 oxygen gives you 1 water molecule. Go to the periodic table, and it's 1.01 for hydrogen times 2 is 2.02. For oxygen, it's 1 times 16.00. So you add up the masses to give you the total mass of a water molecule. 1 water molecule is 18.02 AMU on average, because again, there's different isotopes. But we're not really worrying about isotopes anymore until we get to a further subject where we need them. Okay, and then you just multiply everything by this big number, a big basket of atoms and molecules. So you go from 2 atoms to 2 moles worth of atoms. You go from 1 atom of oxygen to 1 mole of atoms of oxygen. And you go from 1 water molecule to a mole of water molecule. So those are all big enough quantities that we can actually see them and weigh them on a scale and work with them in a lab. Okay, and again, the magic of this specific number is that it turns the mass in atomic mass units into the exact same number in grams. 16 grams, 18.02 AMU to 18.02 grams. And then it's simply saying, if 2 moles, how many atoms is that? Well, 2 moles is 2 times Avogadro's number of atoms of hydrogen. So unit of measure and the substance. 1 mole is just 1 times Avogadro's number of atoms of oxygen, and 1 mole is 1 times that number of molecules of water. So you filled out the table. So now go ahead and answer the questions. They're pretty straightforward. And I'm going to go ahead and do a couple of them with you, and give you the answers to the rest. Okay, so here we go. So how many water molecules in 1.3 moles of H2O? So in 1 mole, there's that many. So 1.3 moles would be this. Okay, again, units of measure, substance, units of measure, substance. And I don't care that you didn't multiply that out. Just that, that shows you what the number is. That's what you want. It's just the concept there. Okay? All right, how many grams is 5.3 moles of H2O? So 1 mole is 18.02 grams. So 5.3 moles is going to be 5.3 times 18.02. Okay, and you could multiply that out. Let's go ahead and do it on this one now. Doing it. I'm not going to worry about significant figures, and rarely will I in this class. Occasionally we'll touch on it. That would be 95.5. It can be only to 2 significant figures, so that should really be 96, but let's just go ahead. We can deal with that later. Again, unit of measure and substance. Okay, so there's your answer right there. Okay, let me do one more, and let's go ahead and do number 10 rather. How many grams of oxygen in 0.002 moles of H2O? So 1 mole has 16 grams of oxygen, so 0.002 will have 0.002 times 16 grams of oxygen. Okay, so let's be sure I'm on screen here. So if you, on 1 mole, there's 16 grams. In 0.002 moles, there's 0.002 times 16 grams, which gives you 0.032 grams of oxygen in 0.002 moles of H2O. Again, it's just scaling like you were working with the recipe in the kitchen. Okay, I'm going to go ahead and give you the answers to the other 3, and you can work those on your own. Okay, and here are your answers to the other 3. How many moles of oxygen in 0.73 moles of H2O? Well, there's 1 mole of oxygen for every 1 mole of H2O. So in 0.73 moles of H2O, there's 0.73 moles of oxygen. Down here, how many hydrogen atoms in 7.3 moles of water? So you have 2 times a mole of hydrogen atoms in 1 mole of water. So if you want to know how many in 7.3, you have to take that 2 times 1 mole in 1 mole of water and then multiply it by 7.31. So it's a few multiplications there. You end up with this number, and then you move the decimal. So it's 8.8 times 10 to the 24th atoms of hydrogen in 7.3 moles of water. Okay, and then down here, how many grams of hydrogen in 0.31 moles of water? So in 1 mole of water, there's 2.2 grams of hydrogen. So in 0.13, you have to multiply this by 0.13. You're just scaling it down. So 0.13 times 2.2 grams, and I told you always include your unit of measure. I didn't there. And that's going to give you 0.63 grams of hydrogen. Okay, we're going to move on to methane, otherwise known as natural gas, CH4. So let's go ahead and fill out the table. Okay, so there's the table, and again, we're interested particularly in this box here, somewhat over here, but really more in this, over in that red box. We're interested in moles, working with moles. So as you start doing these in the future, you skip past this step right here. We're just showing the relationship between this and this in this lesson. You don't even do the molar atomic mass and number of atoms. You just go straight to moles. You're just dealing with big baskets of molecules called a mole. Okay? All right, let's go ahead. So how many methane CH4 molecules in 0.31 mole of CH4? So if you have 6.022 times 10 to the 23rd in 1 mole, then you have 0.31 times that in 0.31 moles. And unit of measure and substance, mole spelled without an E. Okay, so there's your answer on that one. All right, how many grams is 1.9 moles? So let's do that. So 1 mole is 16.05, so 1.9 moles is going to be 1.9 times 16.05. Okay, so there's that number, 30.5 grams of CH4 in 1.9 moles of CH4. All right, let's do one more here, and then I'll just give you the answers for the rest. Okay, how many grams, let's do the last one, how many grams of hydrogen in 6.43 moles of CH4? So in 1 mole of CH4, there's 4.04 grams of hydrogen. So in 6.43 moles of CH4, you'd need 6.43 times that many grams. So that would be your answer. And that gets us to 26.0. So again, so we wanted 6.43 moles, so we needed 6.43 times that number of grams of hydrogen in order to get us the 6.43 moles. Okay, let me go ahead and give you the solutions to the rest. Okay, so let's look at these answers quickly for the ones we didn't do. 16. How many, 15. How many moles of carbon in 0.012 moles of CH4? Well, there's 1 mole of carbon for every mole of CH4, so it's a 1-to-1 relationship, so it's 0.12 moles of carbon. Next one. How many grams of carbon in 1.04 moles of CH4? Well, in 1 mole, there's 12.01 grams of carbon, so in 1.004 moles, there would be 1.004 times 12.01 grams of carbon. Okay, so we just multiply those numbers, and you get a number just slightly bigger than what you had before. It's 12.1 grams of carbon. Finally, how many hydrogen atoms in 18.7 moles of CH4? So in 1 mole of CH4, you have 4 times a mole. So if you're interested in 18.7 moles, then it's going to be 18.7 times 4 times a mole. That will be how many? So 18.7 moles of CH4, and then this is how many atoms there are in 1 mole. So you multiply that by 18.7, and you end up with this number. Scientific notation, you got to make a little decimal adjustment. So it's 4.5 times 10 to the 25th atoms of hydrogen. Okay, we'll move on to the next one. Okay, so here's our table. Check it over. Be sure that's what you got for everything there. So again, we're interested in over here in the moles side. So I'm going to pick a couple of these to do and then just give the solutions for the rest of them. Okay, let's do 20, 21, and 22. So how many moles let's not. It's a 1-to-1 for nitrogen. That's why I'm not really interested in that. Let's do 20. Yeah, let's do these 3. What the heck? Do them all. Okay, how many grams is 4.3 moles of NH3? So 1 mole of NH3 is 17.04 grams, so that many would be multiplied by that. Okay, so there's 7.36 grams of NH3 in 4.32 moles of NH3. All right, how many moles of nitrogen in 6.3 moles of NH3? That's a pretty easy one. There's 1 mole of nitrogen for every 1 mole of NH3. So if you want 6.03 moles of NH3, you need 6.03 moles of nitrogen. 1-to-1 correspondence, okay? I'll just write that one. And then finally, how many grams of nitrogen? Let's do this one down here. It's just a little more involved. How many grams of hydrogen is 3.34 moles of NH3? So for 1 mole of NH3, you need 3.3 grams of hydrogen. So if you want 3.34 moles of NH3, you need 3.34 times that many grams. So let's write that out. Okay, so 10.1 grams of hydrogen in 3.34 moles of NH3. Again, just like scaling a recipe when you're cooking. No different than that. Okay, let me go ahead and give you the rest of the answers. All right, so how many ammonia molecules in 0.103 moles of ammonia? So in 1 mole, there's a mole, 6.022 times 10 to the 23rd. If you only want 0.103 moles, then you multiply that number by 0.13, and it gives you this number over here, which you adjust the decimal. 6.2 times 10 to the 22 molecules of NH3 in 0.103 moles of NH3. Next is how many moles of nitrogen in 6.3 moles of NH3? Well, you can see there's 1 mole of nitrogen for every mole of NH3. That's a 1-to-1 correspondence, so it's going to be 6.03. How many grams of nitrogen in 7.6 moles of NH3? So in 1 mole of NH3, there's 14.01 grams of nitrogen. So if you want to scale that up to 7.6 moles, you need to multiply that number by 7.6 moles, and that'll get you up to 106.5 grams of nitrogen in 7.6 moles of NH3. Last one down here, how many hydrogen atoms in 0.54 moles of NH3? So you have 3 times a mole of hydrogen atoms in 1 mole of NH3. So in 1 mole of NH3 you have 3 moles of hydrogen atoms, 3 times that number. And if you want to scale that down so you only have 0.54 moles of NH3, then you would take this number and multiply it by 0.54. So there you have 0.54 times 3 times a mole, and that'll give you this number over here. All right, one more. Okay, so let's just go ahead and do a quick walkthrough on this. So this is a 3-element compound, so you needed an extra row there, and you have 6 carbons, 12 hydrogens, 6 oxygens to make 1 fructose molecule. That's fruit sugar. And then you go ahead and compute times the molar masses that you get off the periodic table, and you find that this molecule, a single molecule of fructose, has a mass of 180.18 atomic mass units. Now you scale everything up to moles over on this side, so the numbers are the same, but now it's moles instead of atoms or molecules. And the number for the mass is the same, except it's in grams now. And then you just multiply the number of moles times Avogadro's number. 2 times that. And it says 12. It should say 2. No, it should say 12. I'm sorry. It should have been a 12 right there. Okay. And then 6 times a mole, and then 1 times a mole. All right. So how many fructose molecules in 3.1 moles of fructose? So in 1 mole of fructose, there's a mole, that number. So in 3.1 moles, there's 3.1 times that number of molecules, and that gives you 1.9 times 10 to the 24th molecules of fructose in 3.1 moles of fructose. Okay, how many grams is 4.5 moles of fructose? So if 1 mole of fructose is 180.18 grams, then 4.5 is 4.5 times 180.18 grams. So there's the calculation right there, and it gives you 810.8 grams of fructose in 4.5 moles of fructose. And it's just simply scaling things up and down. All right, how many moles of carbon in 2.2 moles of fructose? So in 1 mole of fructose, there's 6 moles of carbon. So in 2.2 moles of fructose, there's going to be 2.2 times 6 moles of carbon. And that gives you 13.2 moles of carbon in 2.2 moles of fructose. How many grams of hydrogen in 1.6 moles of fructose? So again, in 1 mole of fructose, there's 12.12 grams of hydrogen. So if you're interested in 1.6 moles, then you'd have to multiply 1.6 moles times 12.12 grams of hydrogen, and that would give you 19.4 grams of hydrogen in 1.6 moles of fructose. Okay. Next up, how many oxygen atoms in 2.5 moles of fructose? So in 1 mole of fructose, there's 6 times Avogadro's number. So if you're interested in 2.5 moles, you take the 2.5, and then this is the amount that's in a single mole of fructose. That's the number of oxygen atoms in a single mole. But you want 2.5 moles, so you multiply that all together. You get 90.3 times 10 to the 23rd, or slide the decimal over at 9.03 times 10 to the 24th atoms of oxygen in 2.5 moles of fructose. Okay, and the last one. Make sure I keep this on screen. How many grams of hydrogen in 4.4 moles of fructose? So in 1 mole of fructose, there's 12.12 grams of hydrogen. So if we're interested in 4.4 moles of fructose, it would be 4.4 times 12.12 grams of hydrogen, which is 53.3 grams of hydrogen in 4.4 moles of fructose. Okay, that's how you do these. If you still have questions, come to just tutoring hours, and I'm around on Friday and Saturday. Friday 1:30 and 6:30, and Saturday from 8 to 10. All right, we'll see you at the next lesson.